Right. Let's now take on a new type of problem. And in this problem, what we're going to do is we're going to take a container, and what we're going to do is we're going to change things on this container. Now, what that means is we take the original, and let's suggest we heat it up. So now the temperature in this container is now warmer. So we started off with an initial temperature, and then we wound up with a final temperature. But it doesn't have to be just temperature. Perhaps we increased the volume of this original container, or we decreased the volume, or we added more gas to the original container, or we can do any number of things to the original container, container number 1, and we did something to it. And now we have a new situation entirely. And let's take a look at the problem and we can see what happens. It says here that we had a 3-liter sample of air. It doesn't say it, but we assume it's in a container. And what happens is that container that had the air got warmed. It was warmed from 50 to 100. Now, the question comes in, which is, so what is the new volume? Well, what happened to the pressure? It says that the pressure did not change. And it says that the number of particles does not change. So those were held constant during this change process. It was just that the temperature was caused to be changed, and we're asking, so what happened to the air? Well, when we have a situation like that, this is what you think about it. We say, right, this container had a series of pressures, volumes, amount of moles, we had a gas law. In other words, PV equals nRT was related or described this container. But it's the pressure for container version 1, the volume version 1, and the N moles, and then the temperature. Now, when you get the ending container, it too has to obey the gas law because it's a container with gas in it. So we have pressure number 2. There's perhaps a volume number 2. There's a number of moles. And so every time you get a container, the rules of PV equals nRT. Now, as was shown in class, we can maneuver this around. We can say that P1 over V1 over N1 T1 equals R. And we can say that P2 V2 over N2 T2 also equals R. And so what very quickly emerges, which we've had discussed, is that when you have a container and you do something to that container, heat it, change the volume, change temperature, whatever you want to do, when you change the conditions, the PV over NT ratio of the new container is going to be the same as the PV nRT of the old container. They both equal R. Now, I never said that the pressure inside the initial and the pressure inside the final had to be the same, or that the volumes had to match. I never said that. All I'm saying is that the overall ratios must be the same. So why don't we set the two equations equal to each other? And again, this is a thought process that we discussed in lecture. Now, this right here, this is your golden ticket. If you're able to say, right, there was this container initially, and you changed it, this equation needs to come to your mind. And the reason why is because we can now relate all the variables of gases between the initial and the final container. But now you write this down. This is your first move under typical circumstances. You write down this entire equation as you see it. And then you go back and take a look. You say, right, we have a container that has 3 liters in it. And we notice that the temperature is going to change. Now in this case it was nice and it told you that the pressure and the number of particles remain constant. So if the pressure is constant, we can dump the pressure values out. They cancel out. And then the number of particles or the moles can also be dumped. You just built the custom equation for this problem, because there's a lot of other problems that would have changed other things around. So your strategy is to write down V1 over T1 equals V2 over T2. And this is the equation you're going to use to solve this problem. And like before, you write down V1, T1, V2, T2. The volume given is 3 liters. The temperature is 50. Volume 2, that's what you're looking for. The ending temperature is 100. Now you can cut a corner here. When you use this equation, you can keep your temperatures as Celsius, because if you convert them to Kelvin, you would just be canceling out the Kelvin values at the end. But remember, that only works when you're using the changing container equation, not the PV equals nRT. If you're just using this equation right here, you always convert to Kelvin or your overall numbers don't match up. And so now what we do is we plug in our values since we want liters. So 3 liters over 50 degrees Celsius is equal to X liters over 100 degrees Celsius. And when you crunch the number, then the ending volume is going to be 3.46 liters. And that is the answer you are seeking. Let's do another one. Right, here's a new problem. A container is filled to a pressure of 40 atms at 0 degrees with a gas. What is the pressure if the temperature increases to 45? Again, we've got a container, and now something has been done to that container. In this case, we raise the temperature, and they're asking us about the new situation. We saw previously that whenever you get a situation where the container undergoes changes in its condition, we use P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, our next maneuver is to look at the problem and ask the question, what is being held constant and what is being changed? So a container is filled to 40 atm at 0 degrees, and it's asking us for what happens to the pressure, the temperature changes. You go, right, what didn't change was volume. So I can cancel volume from my equation, and I can cancel the number of moles from equation. The result is my equation reads P1 P2 T1 T2. Now my P1 value, my initial pressure, is 40 atm. What is the pressure? That's what I'm looking for. The initial temperature is 0 degrees Celsius, and temperature 2 ending is 45 degrees Celsius. See, now we're going to get ourselves into trouble. We're getting ourselves into trouble because we need to change the temperature into Kelvin. Because if I keep it in degrees Celsius, I already can anticipate that that's going to zero everything out. So in fact, I can't use my shortcut. I have to convert to 273. And I convert 245 to Kelvin by adding 273, which is 318 degrees Kelvin. So now I've matched up and got all my units proper. So now I plug it into my equation. P1, 40 atm. T1 is 273 degrees Kelvin is equal to, I don't know what my pressure is going to be at the end of this. That's what I'm looking for, and it's 318 degrees Kelvin. And when you run it, you get 46.6 atm. That is going to be equal to x. So now I have solved it. Let me point something out to you, and this is a very powerful idea. And the idea is reasonable. In chemistry and physics for sure, once you get an answer, it's always a good idea to ask the question, is it reasonable? Now what does that mean? Well, look up here. The temperature started at 0 and it went up to 45. Now I know that if I increase temperature, I should get an increase in pressure. I started at 40, so I should see the pressure go up. And in fact, I did. Now I don't know if 46.6 is the actual answer, but I do know that this answer is a reasonable answer because the pressure increased as expected. And so it's worthwhile keeping that idea in mind.